Internal shear force and internal bending moment diagram. Internal shear force, we typically express that using V, and internal bending moment, which is expressed in M diagram. This is the basic to beam design, and we follow some steps to solve the problem. Imagine that we have a beam that is simply supported like that. You have a knife edge contact here, and then a rolling contact here, and then a load in the middle of this piece. Typically we express load by using P. So this is the situation, this is the problem. Now step number one to solve, we want to see what's going on inside this piece in terms of shear force and bending moment. And if we know that, then we'll be able to tell whether this thing will fail or not. So step number one is to draw the free body diagram. Draw the free body diagram. So if you draw the free body diagram of this piece, it's gonna look like a beam like this, and then this is reaction. Let's define this point as A and this point as B. This is reaction force at A and reaction force at B. Now in a knife edge contact you also have a horizontal shear. However, in this loading system there is no horizontal force, so there will be no horizontal force. So I'm just gonna have it just for the theory. Now the force here P. So this is the step number one for finding the shear force and bending moment diagram. When I say shear force and bending moment diagram, from now on it means that it's the internal shear force and internal bending moment diagram. Now let's calculate the step number two is finding the, we can actually do it in the previous. So step number two, I want to do it here. Step, let me just have a line there like that. Step number two is find the reaction forces. Find the, or calculate the reaction forces. As you know, to calculate shear forces, reaction forces, you have to apply moment. Apply moment. So let's apply moment at A. Not apply moment, but take moment. I would say take moment at the point A or B. So if we take moment at A, and then nothing is moving here, so summation of all moments at A is 0. So if we calculate, imagine that this beam is x feet long, so you can do x by 2 here, and then x by 2 if it's x feet long, like that. So if we take moment for this RA at this point A, then this will cancel because there is no distance. Then for this P, we'll have a clockwise moment, so that's negative, minus P x by 2. That's the moment distance. And then RB, which is the anti-clockwise. So we are taking moment with respect to point A. So this will be this will make an anti-clockwise moment, RB. So that's positive, plus RB, and the distance is x, is equal to 0. So RB is equal to P by 2. So P by 2 is the reaction at point 2. Let's apply take moment at B. Take moment at B. So summation of all moment at B is equal to 0. Now we are taking moment with respect to this point. So for this P force, it's gonna be anti-clockwise. So that's plus P, distance is x by 2, and then this RA would be clockwise. So that's minus RA, and the distance is x is equal to 0. So RA is P by 2. By taking moment in both reaction points, we can actually verify whether we got these numbers correct or not. So just the verification, we can do the verification right in this box. So verification. So if we sum all the force, that should be equal to 0. So all the forces, so RA, which is P by 2, is a positive force going upward, minus P, which is negative downwards, plus RB, which is P by 2, is equal to 0. So you can see P by 2 plus P by 2, and then P is basically 0. So we did this calculation correctly. So this is step number 2, find the reaction forces. Once we know the reaction forces, then we have to find the point of interest. So step number 3 is find the points of interest. There are 2 points, 2 ways. There are 2, I would say, 2 types of points of interest. So number 1, where the load changes. So change of load, whenever load changes, change of load is 1 point of interest, and then the maximum moment point. So maximum bending moment point. Now maximum bending moment, we cannot is difficult for a complex problem where the maximum bending moment would be. So this is typically found after drawing the shear force diagram. After drawing the shear force diagram. Wherever shear force is 0, moment is max at that point. So at 0 shear, V is 0, bending moment is max at that point. We can find that later on by calculation that each of these points bending moment is max. So this is used some kind of like a rule. So shear force 0 means bending moment is equal to maximum. Now there could be a bunch of different maximum points if the loading situation is complex. For example, a hanging breeze or a breeze that has bunch of reaction at the bottom, and then different types of loading situation condition. We'll see that later. So it's not just one max, there could be a bunch of max in local maximum points. But typically wherever the shear force is 0, that's what the bending moment will be the maximum. So, and then step number 4, once we find these points, step number 4, Once we find these points, then we have to find the internal shear force and bending moment. So now we're ready to find the internal shear force and internal bending moment in our point of interest. So in the previous example, like this one, as you can see here, if we start from point A, and you keep going this way, then I don't have anything going on until this point. Let's define this point as C. So I'm not seeing any change of load until I reach at C. Once I hit C, I see the P forces coming down. So that is a change of load. So there was no load change between A and C, and at point C I have a change of load. So point C is a point of interest in this loading condition. So let's go cut at point C to see what's going on inside. So we know the point of interest. So to see internally, if you want to see anything internal, you have to cut. So cut to see the inside, what's going on. So let's cut that. Now if you have a concentrated load, you have to cut it before and after that point. So remember that for a concentrated load, cut before and after the point. So in this problem, this is a concentrated load, concentrated at point C. It's not distributed, it's just concentrating at point C. So this is an example of concentrated load. If it's a concentrated load, we're going to cut slightly before C and slightly after C. So let's cut before C, point C. When we say cut before point C, I would like to use the notation to the left before point C, or would say to the left of point C, to the left of C, like that. So if we cut before point C, so our beam is like this. If we cut before, we'll see the reaction force here, P by 2, distance is x by 2. This is very slightly before C. So if this is the point, so the distance would be always x by 2, not that different. So if you go here, cut right before C, we don't really see this P force. After cutting, we don't see anything to the right side. So once we cut here like this, we don't see anything what's going on to the right side. Now if you see this force P by 2 is acting upwards, to balance that we need to apply some force downwards. So now the force is balanced. Now you realize that if you do a balancing force, this is creating a couple. So if you don't do anything to this piece, it's gonna keep rotating like this forever. So 2 is not balanced. So to balance that, we need to apply so the clockwise moment was created by applying this V, and then to do a anti-clockwise same amount of moment at that point will actually balance that. So I would like to call it, because we cut to the left, I would like to use that L, VL, and this one is maybe L, VL at point C, like that. Now we can easily find the reaction, shear force at that point. Summation of Fy is equal to 0. So P by 2 is a positive force going upward, minus VL LC going downwards, that's negative, is equal to 0. So VL left, slightly left to the point C is equal to P by 2, like that. So we found that. Now we can also calculate the moments. If we take summation of all moment at C anti-clockwise is equal to 0. So for P by 2 is say clockwise moment. So we are taking moment at this point C. So P by 2 will make a clockwise moment. So that's negative. P by 2 and the distance is x by 2. And then we applied this MCL, which is counterclockwise. So plus MCL at that point to balance it. So the moment at C slightly to the left is px by 4, like that. Now, so we cut to the left and found this shear force and bending moment. Let's cut to the right side. So if we cut to the right side, cut to the right side of C, slightly right, not so much. So if we cut right side at C, if this is the C point, now we'll see that P force because we are cutting to the right. So we'll see that P force now. And then of course we have that reaction force P by 2, distance is x by 2. To balance this force we need to apply V downwards to the right side of C, and then a counterclockwise moment at C, like this to be consistent, like that, like this. So balances that. Now the summation of Fy will give you the VCR value. So P by 2 positive minus VBR to this, that is negative. So VRC is P by 2. That's the weight. We actually got this P downwards negative. We didn't consider that. So consider that. So minus P downwards. So if you do that, that's going to be negative P by 2. So it's actually it will come negative VC. Now let's do the moment calculation. So summation of all moment at C is equal to 0. So for P by 2, it's going to be P by 2 times the distance is x by 2. Now you see that will create a clockwise moment, so I'm going to say negative. Now for this P force, it will also create a clockwise moment, but the value is 0 because the distance is 0. Now plus the moment we applied at that point is equal to 0. So MRC is equal to px by 4. If you remember, we actually got the same value for to the left side. MLC was also calculated px by 4. We can go back to the previous slide to see that. Look at this, px by 4 right here at the corner. It's the same thing as the right side because this point is very close, so there is no distance, so there is no moment basically. So step number 4, we cut it and then calculated it. Now it's the step number 5, which is drawing the shear force and bending moment diagram. So step number 5, draw the internal shear force diagram. So basically make an axis like that x-axis, basically beam distance from left to the right, and then the y-axis should start from 0 because it's a static problem, so it's gonna go minus plus so that it can balance. Now we have to kind of assume that this is, let's say, p by 2, because if you look at point A, this was our point A, and then let's say this is point C and this is point B. If we go back, so that was the problem, so the load diagram. So if we can also draw the load diagram here. So load diagram was like this. So here we got p by 2, and that was p. So if we just draw that here on this graph, let's say this is p by 2, so nothing, so it's going up like this, and then nothing happening until point C. And then at point C, if you remember, slightly before we had positive, we calculated VL to the left side positive p by 2, and then V shear force to the right side we calculated minus p by 2. So it changes the direction immediately, so it goes like positive 2 minus, let's say this is minus p by 2. So it drops from here like that. To verify, if you see this p by 2, that should equal to that concentrated force. Now nothing going on from C to B like that, and then it goes back up again. At B we got positive p by 2. So once you draw that, you have to kind of shade the area to define where the shear force curves, because there will be lots of curves there. Now if you remember the basics, this is the equation, constant force equation, which is P equals constant. So if it's a constant equation, that looks like, so basically if you draw y equals, say, B in XY graph, it looks like this. B is that. So that's the equation. Now we'll have to draw the bending moment diagram. Now before we do that, I would like to call that a tiny step number 6, to find the maximum moment point now. So find the max moment point now. After drawing the shear force diagram, we told before here the shear force is 0, V equals 0. So the moment would be max here. We actually calculated that before. So moment at C to the left was equal to moment of R right side to the point C is equal to calculated px by 2. So px by 2. So at point 2, that's, say for example, in this moment curve, this is px by 2, and then this is x by 2, and then this is, so that's point A, point B, and then that's point C. Now if you see that the moment equation, which is I think it was px by 4, not px by 2, it was px by 4. Let me double check. Yeah, that's px by 4. So the moment, sometimes you have to calculate the moment again after you find the shear force, zero shear force. In this case, we already had that point as one of the point of interest, so we already calculated the max moment. We don't have to do anything. Now at point A, moment is 0 because there is no distance. If you cut here and take moment, there is no distance from force P, so moment will be 0 at point A. You can cut and find that if you want. Also moment at B will also be 0. You can calculate that too. Now if you see a equation like this, px m equals px, so we can say we found mc equals px by 4. So it's something like y equals mx type of equation, which is a straight line through the origin. So the moment equation will look like this, and then go down like that, and then so that's done. So this is the bending moment diagram, and this is the shear force diagram. This one is shear force diagram, this one is bending moment diagram, and both are internal shear force, internal bending moment diagram. And then this top one is called load diagram, like that. So that's it about the shear force and bending moment diagram. You could apply this in any problem to solve internal shear force and bending moment diagram.